Okay, good morning, everyone. I don't have anything to share about the final project, weekly milestones, questions, comments. All good? Okay. All right, so back to this admittedly short module in the course on collective robotics. So we're focusing on the question of there's something out there in the real world that we would prefer to have a machine or machines do for us rather than humans. And whatever that task is, it's beyond the ability of any one robot. Disaster recovery after an earthquake, forest fires, ocean cleanup, usually tasks that span a very large area that by definition can't be performed very efficiently by one robot. So we're going to try and design a collective of robots that can go out and perform the task better than any one robot could do, and definitely not worse than any one robot could do. You've all been parts of groups, some of which function well, and some which you wish you could kind of do everything on your own because the group is actually worse than you, the individual. Not so easy to get teamwork, coordination, cooperation, communication to work well. How does this work in nature, and how do we go about trying to build it into machines? And finally, how do we go about building it into machines automatically by evolving the machines to exhibit teamwork, coordination, communication, and so forth. So we've broken this module down into two parts. In lecture 19, which we'll jump back to in a moment, we're looking at swarm robotics in general. What does that really mean? And we're going to look at some early efforts to do this. And then today we'll move on to lecture 20, looking at a more sophisticated team that is capable not just of teamwork and coordination, but also communication. Okay, so as usual, when we started our discussion of collective robotics last time, we started with a little bit of bio-inspiration. Clearly, Mother Nature has discovered repeatedly over and over again how to evolve autonomous machines to work together in sometimes very large numbers. So it is possible. We looked at arguably the very first attempt to do this. This was work performed by the computer graphics researcher Craig Reynolds, who invented the Boids. The idea in the Boids is you have a bunch of simulated agents or robots. They're all running exactly the same program. That program is made up of 3 separate subroutines, and those 3 separate subroutines for each Boid at every time step dictate how that Boid changes the direction it's heading and the speed at which it moves. And with very, very simple rules, you can code up these little subroutines yourself. You could do it in about a dozen lines of code. If you're a good programmer, you can get it down to 8, 7, 6 lines of code. And you can get, as we saw last time, pretty sophisticated behavior. Collective behaviors that look kind of like what you see in nature. This was a pretty surprising, quite a surprising result back in the 80s. You didn't have to put much into the brains of members of a collective to get them to perform interesting collective behavior. Okay, we ended last time with this slide, which is going to set us up for the experiment we're going to talk about today, which is we're going to go about doing an evolutionary robotics experiment now. The Boids that you just saw, that was a hand-designed controller, but what happens if you have a different kind of collective behavior in mind? How do you go about designing the brains for members of the collective so that they exhibit that collective behavior? The authors of the paper we're about to discuss took inspiration from group hunting in big cats. By definition, big cats are at a disadvantage when they hunt on their own because they have a disadvantageous acceleration curve relative to their usual prey. So not surprisingly, there was and is evolutionary selection pressure acting in certain species of big cats to evolve their ability to coordinate the way that they go about bringing down prey. So, in this paper from 1996, the authors asked 3 different questions. Question number 1, first of all, can we use an evolutionary algorithm to evolve behaviors for a team of robot predators in simulation? And if we can, how exactly should we set up that evolutionary algorithm? What's the fitness function? How does this actually work? And then if we do set up a successful evolutionary algorithm where fitness starts to increase over evolutionary time from generation to generation. If prides of virtual lions get better and better at group hunting, how are they doing it? What mechanisms of coordination evolve? Okay, we're going to see answers to these 3 questions. Let's start by looking at the simulated world that this group hunting is going to take place in. This is 1996, 4 years before physics engines, so no physics engines here. They created in simulation a 2-dimensional grid. Not a grid, it was a 2-dimensional plane. And they placed within this plane at random positions 1, 2, 3, 4 virtual lions. These were not robots, these were just 0-dimensional points that exist in the 2-dimensional plane. And they dropped a 5th point at a random location, G, which is the virtual gazelle. In the experiment, we're going to see in every simulation, the gazelle's behavior is programmed by a human, and the pride of lions' behaviors are going to be evolved. Yeah? Okay. The gazelle at every time step in the simulation is going to move 3 units of distance. And you'll notice that the virtual Serengeti plane here that the lions and gazelles are going to move across is a 15 by 15 unit plane. So this can be 15 kilometers, 15 miles, doesn't matter. The gazelle moves 3 units every turn. And the movement of the lions, as I just mentioned, is going to be evolved, and each individual lion moves 1 unit per turn. So they're building in the top speed of the gazelle and the lion, roughly based on what you see in nature. Okay. This virtual Serengeti plane, which is a 15 by 15 sheet, is toroidal. So imagine this rectangle actually is a sheet, and I bend the sheet so that the 2 long edges touch. So we now have a tube, and now I take that tube and I bend that tube so that the 2 ends of the tube come into contact with one another. We now have a donut or a toroid, which by definition has no edges. So in the rest of this lecture, I want you to imagine these 5 points, the G, the 1G, and the 4 Ls moving on the surface of this toroid. And they can, if they want, from their perspective, move in a straight line forever. They'll never fall off the edge. Yeah, so there aren't any actual edges in the system. It's tricky to draw a toroid and show things moving, so I'm going to just draw it as this rectangle. So it looks like, for example, lion 4 here, if it moves to the east, it looks like it's going to fall off the edge of the world. It won't. It will wrap around and appear here at the next time step. In this particular example, imagine the gazelle is up here at time step T, and the gazelle is about to move 3 units to the northwest. At the same point in time, at time T, L4 is down here in the southeast. It's about to move 1 unit of distance to the east. It looks like G and L4 are very far from one another, but on the surface of the toroid, they're actually very close to one another. So at the next time step, T plus 1, the gazelle is going to land here, and the lion is going to land right on top of it. Good news for the lion, not good news for the gazelle. Everybody see this so far? Okay. So sensing and moving goes beyond the edge of the toroid. So the lion, I haven't talked about the lion or the gazelle, what they can sense yet, but assuming the lion has a sensing radius, we talked about this last time with the boids, this little circle, they can see things nearby, and everything else further away is pretty hazy. The lion at this point in time can probably, at time step T, can probably see the gazelle. Okay, here we go. So let's talk about the gazelle's behavior first, and then we'll talk about the lion's behavior next. As I mentioned, the gazelle's behavior is coded manually using this equation. Okay. We're going to represent the gazelle's behavior as B, and B is a 2-dimensional vector. It's literally this vector here. It dictates where the gazelle is going to move next. In order to calculate B, the way in which the gazelle is going to move at the next time step, we first are going to compute a variable called max, which is the maximum distance on the toroid. This is the maximum distance before things start to wrap around. So if we take our rectangle here, we compute its width and its height and divide both of them by half. You should hopefully recognize this as the Pythagorean theorem. This gives us the length of the hypotenuse for half of the grid. It's this far. So if you take any 2 points and drop it inside this rectangle, the maximum distance between those 2 points is this. Everybody see that? Because remember, this sheet wraps around. Okay, so the furthest the gazelle can ever be from the lion, which is where it would like to be, is max. So far, so good? Okay. All right. So from the gazelle's perspective, we're now going to sum up a set of vectors lowercase v, and those lowercase v's are drawn from a set of vectors. The uppercase reminds us that it's a set. Uppercase V contains 4 vectors, which are the vectors that connect the gazelle at that time step to each of the 4 lions. So in this hypothetical example, here's V1, V2, V3, and V4. V represents the shortest distance from the gazelle to the lion. And when I drew this original slide, I made 2 mistakes, which I've left in to test your intuition. These 4 vectors are meant to represent the shortest distance at this point in time between the gazelle and the lion. Where are the 2 mistakes?
What about like the other direction?
What about the other direction? So you can see I've connected G to L4 with this vector. And hopefully by eye, you can see that this vector is longer than a diagonal spanning half of the rectangle. I'm not sure which one it is, but there is another vector that leaves here and connects. Maybe it leaves here and wraps back around and touches L4 here. That vector is probably shorter. It doesn't matter which one it is. The code will take care of this for us. But the gazelle is able to see all 4 lions wherever they are and to find the shortest distance. It knows its shortest distance to that lion. So the gazelle has a very large sensing radius, as prey usually do for very good reason. Okay, so we're going to sum up all of these vectors. So here's these vectors v, and as we do, we're going to take a weighted sum. We're going to weight this summation as we go by dividing by the length of this vector. We're going to ignore this term for a moment. So we're computing a weighted sum. And after we've taken that weighted sum, we're going to invert the vector. Whichever direction that vector points, we're going to take the vector that points in the opposite direction, and that becomes B, the direction that the gazelle moves at the next time step. The magnitude of that vector is always 3. The gazelle is always sprinting. It's always moving at 3 units. What's the intuition behind this weighted sum? We're trying to give the gazelle a fighting chance here. What is the gazelle doing?
Lines that are closer will have like heavier weight, so it'll affect the direction more.
Absolutely. So let's take L1 here. L1 in this cartoon example is closest to G1. It's obviously going to have the least magnitude of all of these 4 vectors. We're dividing by a small number, which exaggerates the influence of this vector on the gazelle's mode of transport, direction of travel, right? Make sense? You could run away from all the lions. The pretty good thing to do. Smarter thing to do is run away from all the lions, but pay more attention to the one that's closer. Okay, so this is a weighted sum in which the weights are on the denominator. So in order to make it an average, we multiply by this normalizing term, which we don't have to go into the details. Just trust me, this is a weighted average. Okay, this is what the gazelle does. Could the gazelle do anything smarter than this? Run away from the lions, pretty good strategy. Run away from the lions, but pay more attention to the closer lion, better strategy. Did the authors do due diligence by the gazelle? They're going to start evolving lions to try and bring down this gazelle. Could they have made the gazelle smarter? Not a lot of options for the gazelle. It's a completely featureless plane. It's flat. The surface of a toroid is not flat, but from the perspective of the G and the 4 Ls, it is. There's no hills to hide behind. There's no obstacles. There's no hiding spots. There's no other animals around to act as decoys. It's not really a lot here for the gazelle to do, as far as anyone can see, unless any of you have any other ideas. This is about as good as the gazelle can do. Yeah? Okay. All right. Okay. So here's the intuition: sense all the predators and react most strongly to the nearer ones. Let's talk about the lions. Here we go. We are going to start to evolve the brains for 4 lions. We'll talk about the brains first, and then we'll talk about the evolutionary algorithm, how to evolve them. The brains are not neural network controllers. The brains here are going to be tree data structures, like we saw in the previous lecture. Last time we talked about simulated self-replicating robots, and each one of those little modules had a tree inside, a data structure, that it would use to decide what to do next. Exactly the same thing here for the lions, but in this case, the things that are inside the tree are different. They're relevant to the lions. So let's start to create a random brain for an individual lion. We're going to start by making an empty node. And there are then a number of things we're going to place into a bag, all of these things, shake up that bag and pull out from this bag something at random. Let's imagine that we pull out at random rand-dir here. I'll just use R to keep this simple. And that's it. R does not have any arguments associated with it. It's an operand. It's like a variable. So we're done. We don't need to add any additional arguments to this node. Okay. Let's say we take this particular brain and we drop it into the heads of the 4 lions, and then we turn on the simulation. At time step 1, we know how the gazelle moves. The gazelle moves according to this. How do each of the 4 lions move? They move randomly. They move in a random direction, and that direction has a magnitude of 1. The lions always move at 1 unit direction. How well do you think 4 lions with this in their head do at bringing down the gazelle? Not so good, right? Not so great. Okay. Let's now create at random brains for a second pride of lions. Let's shake up the bag again, and this time we pull out G for gazelle, the smallest vector from the lion to the gazelle. Put all 5 individuals back at random positions on the toroid and turn on the simulation again. How do lions with this in their heads do at bringing down the gazelle? What do the lions do in this case?
They just straight line from their current position towards the gazelle.
They all head towards the gazelle. The gazelle does what? Moves away from them. The lions move another step towards the gazelle. The gazelle moves away from them again. Is this any better than the previous pride we just considered? No better. Possibly even worse, right? Hard to say. Not great. All right, let's Again, create brains for our pride. We reach into the bag, and at this point, we grab the plus symbol. The plus symbol requires 2 arguments, so we create 2 empty nodes to indicate that we have to reach into the bag at least 2 more times to create random arguments for the addition operation. We put the plus back in the bag, shake up the bag. Maybe we pull out R this time at random, 0 arguments, that's fine. We reach into the bag again, we pull out G. What does this third pride do? How does this pride behave? At every time step, for each lion, this node returns a random vector. This node returns a vector that points in the direction of the gazelle from that lion's perspective. And then this sum here is a vector operation. So in this case, we haven't seen this before, but this tree is dictating a series of vector operations. So we take this vector and sum it with this vector. We get back yet another vector, which dictates that lion's behavior at that time step. Do the same thing for the second lion, third lion, fourth lion. How does that lion pride behave? What does it do?
So that kind of generally trends towards the gazelle, but like kind of move erratically.
They're moving a little bit randomly, but generally towards the gazelle. Is the gazelle fooled? What do you think? Does this third pride do any better than the first or second? I see a lot of shakes of the head. Probably not, right? The gazelle is having a great time, right? This is excellent, no problem. So we've created 3 different prides at random, and you can already start to guess what the fitness function is going to be, right? How close the lions get to the gazelle. Not so easy for the lions, even though there's 4 of them and there's only 1 gazelle. So I'll stop drawing trees for a moment. Hopefully you get the idea. You'll notice that up here we have 3 different things in the bag that have 0 arguments. So each of these things is a vector. And then we can start to create, or as we'll see in a moment, the evolutionary algorithm is going to start to create larger and larger trees that encode more and more sophisticated vector operations. Most of these should look relatively familiar to you. There's 2 down here that are kind of interesting. These require 4 arguments, 1, 2, 3, 4. So if we were constructing a tree at random and we pulled out if dot, we'd have to fill in these 4 nodes. What does if dot do? Well, when an individual lion gets to this part in its brain, it will evaluate the first and second arguments, whatever they are. And remember that these arguments are vectors. So these vectors flow up into this node. This node is going to take the dot product of those 2 vectors. And if that dot product is greater than or equal to 0, we return the third argument. If the dot product is less than 0, return the fourth argument. So we now have sort of a conditional inside. A lion that has this in its brain can decide or can return different vectors depending on what's going on with these vectors. The lion can in effect say to itself, if this situation is occurring, I'm going to move like this. If it's some other situation, I'm going to move like that. Now, what those conditions are themselves can be evolved, depends on what's down here, and what those 2 different behaviors are, also dependent, can be evolved. Question? So far, so good? Okay. Last one down here, if greater than or equal to, if the magnitude of this vector is greater than or equal to the magnitude of this vector, return this vector up the tree, otherwise return this vector up the tree. So the investigators are throwing into this bag conditionals based on vectors. in the idea that maybe it'll be helpful to an individual lion or possibly the pride as a whole to decide if the situation is happening, then do that. Okay. I'll leave you to read the rest of this. Can you mentally put together a bunch of these vector operations and vectors to create a good brain for the lion, for a lion or the lion pride? If you were out here on the virtual Serengeti toroid and you were very hungry and you had 3 hungry friends with you, what would you do? Maybe circle around the gazelle, and as you said, 1 on each side. So I've got my 3 friends, and we're going to spread out around the gazelle. Let's say I'm lion 3. So lion 1, 2, and 4 is out there somewhere. How do I know where 1, 2, and 4 are? This is the Serengeti plain. There's tall grass out there. I can't necessarily see the other lions. There's nothing in this set that says anything about my fellow compatriots. I can see the gazelle, but with this set, I can't see the other lions. And this is just a reminder that teamwork is difficult. In a lot of tasks where we would like to actually deploy robots, like for forest fires, you have machines that are covering a very large area. They're usually in smoke, so visual detection of other drones is low. In a forest fire environment, satellite connection is very difficult. There are real-world examples where you might have robots crawling through rubble after an earthquake. They can't necessarily see or communicate with their fellow team members, at least not all the time. Part of what makes teamwork difficult. Okay, so a great idea. That's probably a good thing to do. These lions, as far as we can tell, are not capable of it. So we're going to see a set of experiments this morning. This is experiment number 1. How well can lion prides evolve to do with just this material, which isn't great, as you probably already figured out. So in the second experiment, they're going to add 4 more elements to the bag, which is this bag here. So when brains are made for the lion pride now, there are these additional 4 elements that can be built into the tree. These 4 elements are based on an observation from nature, which is a lot of what sensing that goes on in nature is known as deictic sensing. Deictic sensing means I'm not just sensing things that are absolute, but they are relative. So I can sense that there's a light source up there. I can sense that light source is above and more or less in front of me. So I'm seeing something out there in the world that is relative to me. It's not absolute coordinates. In fact, most of what we sense or how we interpret what we're sensing is deictic. It's relative to me or possibly relative to someone else that I care about. I know that about a third of you cannot see the light source coming from the projector, and some of you can. So I can also relatively easily compute some of this deictic sensing of some stimulus in the environment relative to other compatriots. Okay, so let's look at deictic sensing for the lions. First one is they threw in a new vector called nearest. This is a vector from the lion nearest the gazelle to the gazelle. Let's create a brain for our lion pride that just contains that. We've got the 4 lions. Each one has this in its head. So at every time step, each of the 4 lions is moving along the vector from the lion nearest the gazelle to the gazelle. If I am lion number 3, and at a given point in time, I'm the one that's closest to the gazelle. I can see lion 1, 2, and 4. I can see the gazelle. I can see that 1, 2, and 4 at this moment in time are furthest away from the gazelle. I'm the closest one. I move closer to the gazelle. What do the other 3 lions do? At this point in time, they can see that they are further away from the gazelle than lion 3. What do? How do they move?
The exact same way that the nearest one.
They do exactly the same thing. Not necessarily a smart thing to do, but that's the idea. Okay, you can see how for lion 3 that kind of made sense. Whether what 1, 2, and 4 is doing is helping L3, probably not. Okay, but it is deictic. It's relative. Me as lion 3 to the gazelle, lion 1 to the gazelle, lion 2 to the gazelle, lion 4 to the gazelle. That's deictic sensing. Okay, second one is lion, a vector from the lion to its nearest neighbor lion. What happens? How does a pride behave when they're all running this in their heads?
They'll just walk towards each other.
They walk towards each other, possibly. Can we be a little bit more specific?
Or they'll.
It's kind of like the boys. It's kind of like cohesion, but not quite.
Each one has its own nearest neighbor vector, so they'll all kind of join up and form pairs.
They join up and form pairs. There's only 4 of them, so there'll be 2 pairs. Again, on its own, not very smart. Not going to bring down the gazelle, but maybe part of the building block of a better solution. Okay, our lion, so I'm lion 3, and I moved in this direction at the previous time step. At the current time step, I start sweeping to the right, clockwise. Is it clockwise? Yeah, clockwise. And then the first lion that I see in my clockwise sweep, that node returns that vector. L lion, I'm lion 2, and I moved in this direction at the previous time step. At the current time step, I start sweeping to the left, and the first lion I see in this leftward sweep, in this counterclockwise sweep, return a vector, return that vector. So they're going to throw in to this bag the ability for lions to base their behavior on what their other compatriots are doing. We're going to see some A/B testing in a moment. A is evolve lions with this set of abilities, and let's see how good they get at bringing down the gazelle. B is let's evolve lions with this set plus this set, and C, can evolution produce any better prides of lions? And we're going to also see we're also going to see experiment C. In this case, they're going to take the base set and throw in these additional 4 elements to the bag. This is name-based sensing or absolute sensing. This is no longer the lion on my right, the lion on the left. It's lion 1, lion 2, lion 3, lion 4. Let's assume we create a random brain and we drop that into each of the 4 lions, which is this. What does L3 do? How does lion 3 behave in the pride? L3 returns a vector from the current lion to lion 3. It doesn't move. If I'm lion 3, this always returns the null length 0 vector. I don't move. L4 will always move towards lion 3, as will lions 1 and 2, and they'll all just move to wherever L3 is and then stop moving. Actually, they don't stop moving because they always move length 1. So they'll bounce around L3 forever. Yeah? Again, on its own, not necessarily the best thing to do. Okay. Group hunting, team sports, based originally on group hunting. It's an abstraction of group hunting. If you've ever participated in a sport, some sports rely on deictic sensing. Most of what you do, if you're good at that sport, depends on what a fellow teammate on this side of you is doing or this side of you is doing. Other team sports, it's follow the person with the ball. That sort of name-based sensing, that person. Sometimes, or most sports, it's some combination of the two. And if you think about it, a lot of the group activities you've participated in over your life, possibly consciously or unconsciously. You're doing some combination of basing your behavior on deictic and name-based sensing. Yeah? Okay, so we're going to see 3 experiments, A, B, and C. Evolve lions with this is A. Evolve lions of this plus this, experiment B. Experiment C, evolve lions with this plus this. Anybody feel in a betting mood this morning? Which of these 3 experiments, A, B, or C, is going to lead to the evolution of better group hunting, if any of them? Which of these 3 experiments is likely to perform the worst, make it most difficult for the evolutionary algorithm to evolve group hunting?
Assume just one.
This one, right? A is probably going to be pretty bad. There's not much the lions can do. So in this experiment, they're also going to test if we want a whole bunch of robots to work together, is it better for them to do things deictically or in absolute terms? Name a leader and everybody knows who that leader is, and so on. Let's see. Okay. Before we look at the results, there's one other wrinkle in this experiment. This is the first time that we've seen the evolution of groups. So this is a little confusing. At the beginning, we have a population of random trees, like we've seen before. But for each individual tree, we have a pride of lions. So we have a group, which is the population of things that we're trying to evolve to be good solutions to our problem. And each element in that group is itself a group, in this case, a pride of lions. So keep this in mind for today's lecture and lecture 20. We're evolving groups of things. Yeah? Okay. So how do we do that? If we have a particular tree over here, the simplest thing, which we've been doing on the board for the last few minutes, is cloning. Take that random tree, make 3 identical copies of that tree, and take those 4 identical trees and drop it into the 4 lions. As we've just seen, that doesn't necessarily mean that lions with exactly the same brains do exactly the same thing, because each individual lion has its own unique experience. This is the vector that connects me to the gazelle. This is the vector that connects me to the gazelle. So far, so good? Okay. So they're going to conduct evolutionary experiments using cloning. And again, how well do the prides evolve to do when they're all running exactly the same algorithm in their heads? In the second experiment, they're going to do something different. Each individual in the evolving population is still a tree, but now the root node is empty, and every tree has 4 subtrees, where each of the 4 subtrees is the brain for lion 1, 2, 3, and 4. In my little cartoon here, I want you to imagine a population of trees, and I'm showing you tree 1, tree 2, tree 3. In each of these 3 trees, the 4 subtrees is just an individual node. That's just because I got lazy in drawing here. You can imagine each of these is a tree with more or less nodes in it. So the main difference immediately you should be able to see between this experiment and this experiment, we're still going to have a pride of 4 lions, but they all have possibly have 4 unique brains. They're all running different algorithms in their heads. Let's assume that some of these prides do a relatively poor job at bringing down the gazelle. They're deleted from the population. Let's imagine these 3 trees survive. They produce pride behaviors that did a little bit better at bringing down the gazelle. They survived. We haven't talked about the fitness function yet. How do we take the genetic material from these 3 prides and propagate it into the next generation? Well, what we can do is start to create a child pride that again has an empty node at the root. We now need to create 4 subtrees. So we can reach into the population and look at all the survivors, grab a survivor at random, grab one of the 4 subtrees at random, copy it, and as we copy it, make some slight mistakes, make a randomly modified copy, and plug it in to a random slot underneath. So we can mix and match different brains from different prides to create, in this case, a fourth pride, where now the lions in this pride are exhibiting behaviors that were seen in their parents from different prides. Not surprisingly, this is called free breeding. So different members from different prides can copulate, produce offspring. Those offspring grow up together, become friends. They go off and form a pride of their own eventually. So far, so good? Okay. A third way we can do this, it's very similar to free breeding, but in this case, when we have a child pride and we're trying to find the first member of this pride, we only copy into this first position a prospective lion 1 from one of the parents. So L1 in any one of these 3 parents can become L1 in the child pride, but none of their 2, 3, or 4 can. We've now placed L1 in here. We need to create a second lion in this child pride. We go looking at the surviving parents, and we randomly select L2 from one of these prides. This is called restrictive breeding. Why did the investigators do this? Why didn't they stop with free breeding? What's the intuition behind restrictive breeding? These 3 prides here, by definition, survived. These teams are working relatively well within each individual pride, and they're going to collectively produce a new pride, and each one donates a randomly modified copy of itself. It spawns a randomly modified copy of itself, but it goes into the same position.
If they're doing like name-based sensing, I feel like it makes sense to have like a little bit more like intentional behavior. Like it's so consistent.
Excellent. Intent, we'll put scare quotes around things. Intentional behavior. Yes?
Since they all like separately evolve each lion's brain, there's a good chance that like each one of the lions might have a specific role.
A specific role, otherwise known as division of labor, right? So inside a well-functioning team, you see a lot of things going on. You see teamwork, coordination, possibly communication, and in some cases, division of labor. I'm the one doing all the talking in this semester. We don't take turns because I've got a little bit more expertise with this topic. I have very specific knowledge that I'm trying to offload onto you. We as a species kind of coordinate our actions through division of labor. It's not very efficient if everyone in the team learns how to do everything. It takes a long time to learn that, and then anyone can do anything. There's a benefit if everyone can do everything, but there's also a significant cost. Better to try and set up a situation where some members over time get better and better at specific things, and you just make sure that whenever you create a team, you have enough specialists. You need a copy of everything. So the intuition behind restrictive breeding is maybe, even in this very simple situation, there may be a benefit to division of labor. Maybe yes, maybe no. It's a hypothesis. Okay. All right, here we go. Now we're going to talk about results. In this case, in the results reported in this paper, they ran their evolutionary algorithm 1,200 times. They created random populations and evolved for a set number of generations. That's once. They went back, created another random population, ran it again. They did that 1,200 times. It's a lot, so we're going to take this slow. The first 100 evolutionary, they did 100 runs for each of the 3 sensing capabilities. These are the 3 different bags and the 3 team construction methods. So apologies, I'm going to jump around the slides a little bit. So for example, this sensing capability and free breeding. This situation, this sensing capability, and cloning. So we've got 3 different sensing capabilities for the prides and 3 different ways for those prides to propagate genetic information into the future. So that's 3 times 3 possible experiments they could perform. So that gives us a total of 9 different experiments so far. So this is not A/B testing. This is A, B, C, D, 9 different experiments. Everybody see that? For each of those 9 experimental settings, they performed 100 evolutionary runs, and they recorded the average ability at the end of each of these runs, the average ability for the most fit pride to bring down the gazelle. So which of these 9 combinations led to the evolution of the most coordinated, the best teamwork? Okay, that's 900 of the 12 experiments. They also performed a set of controls. So this is good experimental design. A control experiment is, I'm interested in a particular phenomenon, such as deictic sensing. I'm going to run some control experiments which are as close to the actual experiment as possible, but I'm going to control for, or I'm going to remove the one thing that I'm interested in and see how well that control does. If that control experiment does significantly worse, that's proof that the thing that I was interested in, like deictic sensing, is helpful or useful. It's a way to identify or isolate how things you're interested in, phenomenon you're interested in, impact the system that you're looking at. In this case, they looked at 3 different controls. Let's actually start with this one here. This is the simplest control. 1 randomly moving lion. So they evolved brains for this individual lion by pulling things out of this bag, and they evolved populations of those trees for that individual lion, and they wanted to see how well evolution did at evolving. Oh, sorry, I misspoke. This is the 1 randomly moving lion. So they just tried out 100 different randomly moving lions, one after the other. That's what the run means here. There isn't any evolution at all. As you can imagine, none of those 100 randomly moving lions ever came close to bringing down the gazelle. It's a control experiment in which they've knocked out or controlled for most of the things they're interested in. Teamwork to begin with, because there is no team, deictic sensing, they just remove, this is sort of the baseline. What kind of fitness values do you get for this? And do any of these other 11 experimental settings ever do better than this? If none of the other 11 experimental settings ever do better than this, then none of those things helped. Okay. In this case here, they added back in teamwork. So now we still have randomly moving lions. So they evaluated 100 randomly moving prides, one after the other. Do you think this control did any better than this control? Maybe, maybe not. The randomly moving pride, they're probably spread out across the toroid, which means there's less places for the gazelle to quote unquote hide. So maybe yes, maybe no, but probably not much. Okay. Third control, they evolved brains for an individual lion. How well can an individual lion evolve to bring down the gazelle on the toroid? So we're going to get back numbers for these 3, and each of those 3 numbers is an average. How well do these entities do at bringing down the gazelle? And then in these remaining 9 numbers that we're going to see in a moment, are any of those 9 numbers higher than these 3 numbers? Okay, here we go. Oh, sorry, still building up here. They ran their population for 51 generations. Why 51? We have a random population, and then they did 50 more generations. At any given time, they had a population of 500 prides. They let these trees grow to become up to 70 nodes, and if any trees were deeper than 17, they cut things off. Why 70 and 17? This is a historical accident. Some of the very first experiments with genetic programming, evolving trees, which we saw towards the beginning of the semester. That approach called genetic programming was introduced in 1992. The investigator at that time arbitrarily picked these numbers, and everyone's kind of used them ever since. Okay. Okay. Sometimes trees are created by crossover. They can also grab bits of lion brain and swap them, sometimes mutation. When you're copying a tree, grab a node in that copied tree at random, delete that node, the rest of that subtree, and reach into the bag again. Again, we saw crossover and mutation in the lecture on evolutionary algorithms when we discussed genetic programming. Okay. We talked about this before. Every time we evaluate a team or a pride, we place the gazelle and lions at random on the toroid, and each of them moves for 15 time steps. So the number of time steps in the simulation is 15. Final detail. Here's the fitness function at long last. At the end of the 15 units, at the end of the 15 time steps, we take the position of the gazelle, we find the lion that's closest to the gazelle, and take the Euclidean distance between them and subtract 1. Seems odd. If a lion moves, if the nearest lion is less than 1 unit away from the gazelle, fitness is 0. When they run this evolutionary algorithm, are they evolving prides to have higher values or lower values? Lower values. So this condition fires when the nearest lion is further than 1 unit distance away from the lion, from the gazelle. They subtract 1. So imagine a given pride where the nearest lion is 1.3 units away from the gazelle. 1.3 minus 1 is 0.3. If that pride produces a child pride, and that pride gets its nearest lion 1.2 units away from the gazelle, at the end, 1.2 minus 1 is 0.2. Better. We're trying to approach 0. You get 0 if you're there. Oh, sorry. If the lion is less than 1 unit away. So close is good enough in this case. I don't really think they needed the minus 1. It's a little bit mathematically inelegant. You get the idea. The closer the nearest lion is to the gazelle, the better. Okay, now we're ready to talk results. Any questions about experimental design before we do? Question?
Is that minus 1 just a penalty for like if the line is too far away?
Yeah. You'd think so because but lower is better in this experiment. So subtracting 1 kind of helps. It's not very good mathematical form.
Could it be like trying to like make it so that the lion like simulate the lion being able to like have a burst of speed, like, kind of like what we talked about at the beginning?
Maybe.
I feel like it's like a really poor job of it.
Maybe.
I think probably it's trying to minimize the discrepancy between like a successful lion that got like less than 1 unit away and then a lion that was like 1.2 units away.
Yeah.
Because they don't actually behave that differently.
Good point. Yeah, exactly. Maybe it just pulls the non-successful and the successful ones closer together. That might be. Yes?
I would think it's just for clarity to keep the actual, like the value of the fitness the same as the actual distance in units.
Maybe. Oh, yeah. It's also because the lions move 1 unit of distance.
Well, just for like clarity's sake, if the distance is without the minus 1. Actually, never mind.
Yeah.
I thought about that for a minute.
Could be. Scientists aren't perfect. Could also just be a mistake. Maybe we might not need it.
It could just be that, like, I think you mentioned the gazelle moves at like 3 units per step or whatever.
Yep.
It could just be that like the simulation overshoots a lot. So if
Maybe. Yeah,
they're
interesting.
trying to round down the
Yeah, it could have been that at the previous time step, the nearest lion was closer. Possibly. Okay. Maybe someone wants to code this up. It's not too complicated, actually. Could give it a try. Okay. Let's look at some results. Okay. Again, 1996, I'm afraid there's no YouTube videos, so we're going to have to do this with numbers. Here we go. Okay. Here's all the results. We're going to unpack this a bit at a time. Let's make some observations. Let's start with observations about the control results that are reported down here. Here's control 1, 1 evolved lion, 1 random lion, 4 random lions, and here's the 3 averages. Remember that for each of the 3 controls, they replicated that control 100 times, which gives them an average and a best. So on average, let's start over here. On average, 1 randomly moving lion at the end of those 15 time steps was 7.87 units away from the gazelle. Okay, let's do some high school math. Remember that the rectangle, the square, was 15 by 15. We turned it into a toroid. I told you what the maximum distance is on the toroid. How is the randomly moving lion doing? It's doing bad. How bad? About maximally bad, right? 15 squared plus 15 squared, you take the square root of that, and somewhere around this number. The gazelle's showing off, right? It says, I'm as far from the lion as I can possibly be on this toroid that you put me on. So, okay, that's why we do control experiments. That's it. The worst you can do is the worst you can do. All right, so let's try and do better than this. Let's see. Let's look at the other 11. Okay, let's go to the evolved lion. They ran 100 evolutionary algorithms where they were evolving trees for an individual lion. And on average, at time step 15, this is how close the single evolved lion was to the gazelle. Better? Anyone taking a stats class? Good, I see shakes of the head, right? The averages are different, but if you look at the averages and you look at the best, probably not. If we were to do a statistical test and get back a p-value, something that would tell us how confident we could be about whether these numbers are different, I'm guessing that statistical test would say, don't fool yourself. They're not really that different. Again, that's fine. Kind of matches our intuition, right? Not much that a single lion can do. How about 4 random lions compared to 1 random lion? I still don't have a p-value for you, but this definitely does look better. Certainly not due to the innate intelligence of any member of these prides. They just are moving randomly. They spread out across the toroid, less space for the gazelle to hide. So if the pride is brainless, this is baseline. So now when we start to look at the 9 experiments up here, we're looking to see if any of those numbers are better than this number. Here are the 9 averages, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have the 3 different sensing capabilities on the 3 rows, and the 3 ways in which parent prides can spawn child prides. Those are the 3 columns. Across these 9 averages, are any of those evolved prides doing better than random prides? All of them, yeah? So even in this simple, very, very simple environment, there is an advantage to evolving behaviors for groups of robots. There's lots of ways for these simple prides to move in non-random ways, or possibly partially non-random. Maybe a little bit of randomness is actually helpful, but it's certainly better than completely random motion. Maybe that seems kind of obvious, but it is worthwhile pausing for a moment to think about that even in simple environments, evolving groups to do something produces behavior better than any one individual. Okay, let's dive in and look at these let's have a look at these 9 averages. There's lots of observations you can make about these 9 averages. We'll just look at a few of them. Let's start with cloning. That's this column over here. Cloning is the simplest thing, right? The 4 lions are running exactly the same brain. In cloning, name-based sensing, which is this row here, name-based sensing was worse than deictic sensing. You'll have to trust me that these 2 averages actually are different. Why is it worse for a set of clones to do things based on actual names or absolute, lion 3, versus deictic sensing?
So they're all doing the same thing, there's not really any need to distinguish them for most situations.
They're not necessarily all doing the same thing. They all have the same brain, but they might be behaving differently. This is kind of a subtle point. In name-based sensing, in a set of clones, they may all be referring to L3. In the case of deictic sensing, when they're all clones, they're looking at their right-hand neighbor and so on. It turns out that somehow that's that's a better thing to do. You mentioned an idea before, which is they all circle the lion, right? So they're all kind of, back to your previous point, they're all kind of doing the same thing, encircle the lion. And the way in which they can instantiate that circling behavior is to all do the same thing. Here's the lion on my left. Here's the lion on my right. I'm a little bit too close to the one on my left, so I'm going to move apart. That's kind of a good heuristic that would work for all 3 of them. So if you're a clone, doing things in a deictic manner makes sense. If you're all clones, you all have the same brain, and you're referring to L3, you might be L3 versus someone else who's not and is doing something relative to L3 doesn't tend to work very well. So it doesn't matter if you remember the details of that, but it's just an observation that how members of a collective sense one another and the heuristic that they're running while they're participating in a team, it matters. Different combinations of these things makes a difference. Let's have a look at restrictive breeding here, which is column 1 here. For restrictive breeding, the opposite is the case. In this case, name-based sensing prides do better than deictic prides, or prides that can't really sense their neighbors at all. Why the flip? And it turns out that actually this combination, restrictive breeding plus name-based sensing, ends up being the best out of all the 12 experiments. Why?
Just like what we were talking about before, it's like it evolved like division of labor.
Exactly. Yeah? So this result strongly suggests this is happening. It's not clear who, and it probably doesn't matter. L1, L2, L3, R4. Somebody is specializing to do something. And it may also be that someone else in the population is specializing to do something else. It's not clear. It could be useful to have one leader, so to speak, and the other 3 do more or less the same thing. They're basing what they do based on what the leader is doing. That's one possibility. Could also be that there is no leader, but there are 4 different specialists. One sneaks up on the gazelle from the gazelle's back left. Another one always sneaks up on the gazelle from the gazelle's back right, no matter where the L's start or where the G's start. And then some other lion is always the one that chases the gazelle, and the 4th one also chases the gazelle from the opposite direction. Who knows? Unclear. I love this paper and I hate this paper because this is where the paper ends. They never show us what these actual strategies are. Would have been great to see. Okay, question.
So is it true that none of the lions ever caught the gazelle then?
Gazelle is moving at 3 units per time step, pretty fast. So these lions are still mostly going hungry. Not all of them. There's some prides that end up very, very close to the gazelle, but not quite. Question.
Is it the same person who joined the gazelle throughout all of these experiments?
It's always the same. The gazelle is always weighting the direction in which it moves based on the one that's closest to it. Okay. A pretty simple experiment. You could kind of code this up maybe in an afternoon, but you get already some sophisticated behavior. You get some group behavior that wasn't programmed in. They didn't put division of labor in. Evolution, under the right conditions, can find it, as she did in nature many times before. Okay, interesting to think about all the future directions you could go with this experiment. You could evolve the behavior of the gazelle as well. If you did, you would be creating what's called a co-evolutionary algorithm, which we don't have time to talk about in this class. Everything we've talked about so far is an evolutionary algorithm. We have a population of things that are evolving. In a co-evolutionary algorithm, imagine we have two populations, and the fitness of any individual in population 1 is dependent on the fitnesses of individuals in population 2, and vice versa. That's a co-evolutionary algorithm. Fun to play with. What else could we have done? What else could we do? Maybe put some obstacles in the environment. What might the lions and or the gazelles evolve to do when there's other things out there other than lions and gazelles? Maybe deception, occlusion, hiding, feinting. It looks like I'm about to go this way, but I actually go this way. Lots of other things you could build in, and then you could run the experiment to see if evolution can find behaviors that exploit those complications in the teams or the team's environment. Okay. Let's think about the lions for a moment. We've given the lions a little bit of a leg up, no pun intended, by giving them abilities to sense what's going on the Serengeti Plain in better ways. Is there anything else we could have given the lions to make them more competitive? As was pointed out, they certainly weren't optimal. They didn't always bring down the gazelle. They're still struggling. What else might be useful to the pride? Aside from making them go faster, because that's cheating.
Maybe the position of the other lines.
They know the position, in name-based sensing and deictic sensing, they know the positions of the other lions, at least relative to themselves. Maybe their absolute position could be useful, maybe. What else?
Are you saying like what else could we add to it, or what that's already there could we improve on?
Let's say you're one of the lions on the Serengeti Plain. You're very hungry. You got 3 other members. You can see the 3 other members of your team. You can see the gazelle. That's it. That's what you get. What else would you like to be able to see or sense or know that might help you become less hungry in the future?
It'd probably also be helpful to know the orientation of the gazelle to predict what their next move is.
I know what the position of the gazelle is. I, as the lion, don't know where the gazelle is going to go next. We, as the coders, from the God's eye view, we know where the gazelle is going to go next. The lion doesn't.
Maybe like memory to like know how the gazelle typically behaves.
So in the trees that we built, there's no recurrent connections. There's no memory. None of the nodes said the direction that the gazelle moved previously. Or there's also no memory about what did my 3 other team members do at the previous time step. Again, think about any experiences you've had with group sports or any other coordinated activity. If you're in an orchestra, what are the kinds of things that you're paying attention to other than the music itself or where the ball is? You're usually paying attention to the other member. If you're good at the sport or the instrument, you're pretty good at paying attention to other members of your collective. But what? What exactly is it that you're attending to?
You're trying to match your behavior to theirs.
And how do you know what theirs is? You're trying to match your behavior to theirs. So some memory is useful. I saw the person on my left just do that. I saw the person on my right just do that. Helpful to know what happened in the past.
I feel like some like prospection would be good.
Prospection. Remind us what prospection is.
Like
prospection. If you're really good at the sport, I know that left just did this and just did that, and for half a second I looked over and they looked back at me and they signaled in some way about what they're about to do next. I might not be exactly sure from that half-second glance what they were communicating to me, but if I'm good and they're good and we're good, I can prospect. He or she did that, he or she did that. I think he or she is about to do this, and I think he or she is about to do that, so I'm going to do this, and I'm going to give a quick glance to both to signal to them what we're about to do. There is little to no signaling or communication capable in this experiment. So we've only got 5 minutes left, so we're going to just start in on this next experiment in lecture 20 here. Again, we're going to look at the evolution of coordination, but also communication. These particular agents are going to have the ability to evolve signaling between themselves, and we're going to see whether or not that helps and what kinds of signaling, if it's helpful, evolves. This is the one and only experiment we're going to see in which the agents have sex. So we're going to look at female and male agents. This particular experiment, also quite old now, but still kind of interesting, also bio-inspired, not by flocking or swarming or schooling, but by signaling. Males and females, think songbirds here. Lots of communication occurs among different species that are capable of coordination. We are doing it right now. Okay, so let's just set this up. Again, we have a toroidal situation. So imagine a donut, and on that donut, there are a total of 40,000 elements. So this is a grid. All of the agents here are going to move from one grid element to the next at a time. They can move one unit. We're going to drop inside this donut that has 40 empty slots. We're going to sprinkle 1,600 random agents to start. 800 of them are female and 800 of them are male. As you can see here, the males and females have non-overlapping sensor motor capabilities. Kind of an odd thing to do. Again, we see this in nature, sex-differentiated species. Some of them have greater, lesser capabilities along different sensing and motor capabilities. In this particular experiment, seems kind of arbitrary, the females are deaf, they can't hear anything. They're immobile, they cannot move, but they can sing. They're going to emit sound into their environment. Males are kind of the complement. Males are blind. It should say also up here, and females can sing and see. Males cannot see, but they can hear. They cannot signal, they cannot sing, and they are mobile. What do you think the fitness is going to be in this evolutionary setup? We have females that are immobile and can sing, males that are mobile, cannot sing, but they can hear.
Not a singer, like best hearer.
Okay, maybe. Best in what sense? What counts as a good song or a good listener?
Can hear the farthest amount of squares, or...
Okay. Okay, so hearing acuity, how well can you hear? So what? What does it matter in this evolutionary setup, do you think? What's the benefit of being able to hear well? Navigation. For what purpose? I hear well and I'm going to base how I move based on what I hear. Doesn't seem to be useful in and of itself. The fact that there are male and female agents is a very strong hint.
I would guess that the females are trying to communicate to the males to come towards them.
That's it. Absolutely. This is arguably the simplest and the most biologically realistic evolutionary experiment we're going to see in this entire semester. Fitness is reproduction. Males and females that can literally get together produce offspring. Males that don't find any females do not produce offspring and eventually run out of luck. Okay, so stay tuned. Next Tuesday, we're going to see robots having sex. Tonight, you have a quiz due. You're working on your 4th weekly deliverable. Have a good rest of your week.